Good day, viewers. I am creating videos to support teachers of mathematics in using manipulatives and visuals to help learners make sense of mathematical concepts and the procedures and processes that arise from them. And today I'm going to look at the idea of the nth term of a linear sequence and linear sequencing in general. Now, there are different processes that people use for finding and using the nth term of a sequence, but the one that I'm going to look at is in relating any other linear sequence back to the sequence of natural numbers. So when I start with learners and start looking at this with my pupils, I will introduce them to the sequence 1, 2, 3, and so on. And we'll talk about the fact that in general, this sequence is known as n. And you can see that I've built that on the left-hand side of the screen here out of algebra tiles. 1, 2, 3, and so on up to a general term, n. And we'll talk about some of the properties of this sequence, and in particular, the key property of this sequence in that its value and positional number are equal. So the first term is 1, the second term is 2, the third term is 3, and so on. The nth term is n. And so the idea here is that if I can relate other linear sequences back to this sequence, then I can automatically relate them to the position of the term, and I can create a position to term rule in terms of n, because I can relate another sequence to these numbers, and these numbers are automatically related to their position in the sequence. So from there, we'll have a look at some other sequences based on n. We'll look at, say, this sequence. Three, four, five, and we can show what's happening here using the algebra tiles. So how have I turned this 1 into 3? Well, to turn this 1 into 3, I've added this extra 2. And to turn this 2 into 4, I've added this extra 2. And to turn this 3 into 5, sorry, I've added this extra 2. So in general, I'm going to be adding a row of 2 to the bottom of my n. And so we can see that the nth term of this is simply n plus 2. And similarly, instead of adding terms to n, I might subtract. So I might say, well, what about the sequence 0, 1, 2? And I can do the same thing. I can say, well, to make this 0, I'm going to need to subtract 1, and I'm not going to 0 pair those at this point because I want to be able to see the original 1, 2, 3. And to make this 1, I'm going to subtract 1. And to make this 2, I'm going to subtract 1. So in general, what I've done here is subtracted 1 from each term. So this must be the sequence n minus 1. And then at some point, of course, what we'll move to is we'll move to creating sequences of multiples. So I might then look at the sequence, say 3, 6, 9. And say, well, how am I creating that? Well, and I'm going to actually be putting these underneath now so I can see the 1, 2, 3 and separately. So to go from 1 to 3, I might do that. And then to go from 2 to 6, sorry, I might do this. And then to go from 3 to 9, I can do this. So then in general, what have I done? Well, what I can see here is that this 1 has been replicated 3 times. And here this 2 has been replicated 3 times, and this 3 has been replicated 3 times, so that in general, this n has been replicated 3 times. And so now I can start saying, well, that must be then 3n. And we can talk about this one a little bit in terms of, what's happening, what's changed, the fact that this was going up in 1s and this is going up in 3s. Can I see why that is? Well, yes, because every time I'm adding 1 to my n, I'm adding an extra column of 3. And so it's that's telling me that this is based on 3s and the 3 times table. And when we've had those sorts of conversations, I can say, okay, well then what about this sequence? Well, if I look at this sequence then, I can say, well, it's going up in 3s. So actually, it's related to the 3 times table. And through the 3 times table, it's related back to n. So through this sequence 3n, it's related back to n. But what would I do now, not to these numbers, but to these, to generate this sequence? Well, again, I'm sure you can see, to here, I would add an extra 2. And then similarly to here, I could add an extra 2. And, don't get confused here. Some people might start thinking, well, this means 4n. Well, it looks like it here, but it's not everywhere. This is not 4n because of the extra 1. This is 4n, but then it's not 4n there either. What we're seeing here is for every one of these, I can make 3 rows of my number. So 3 1s, 3 2s, 3 3s, and then I'm adding an extra 2. So I'm adding an extra 2. So in general then, this must be 3n plus 2. Now, one of the benefits of working with learners in this visual and concrete way with sequences is that actually we can start to get a bigger sense of the underlying structure of these numerical sequences and of what's happening here. So what I can do now is I can build a numerical sequence, let's say something like this, or even, that would do nicely, and start saying, okay, what about this then? What might the nth term of this be? What might the nth term of this be, of this sequence? How can I build something using my n's that mirrors the patterns that I'm seeing in this sequence? And I can see that here I've got, well, in each sequence, I've got 1, 2, 3, 4, 5 rows of my n. So here I've got 5 rows of 1, here I've got 5 rows of 2, here I've got 5 rows of 3. So in general then, I'm going to have 5 rows of n, and I can see the sort of fiveness calling to me in these sequences. And then I can see that there's an extra bit underneath, which once again is my plus 2. So this sequence must have the nth term 5n plus 2. And I've not actually written down the numbers here. I've not written down what those numbers are in order to evaluate that sequence and in order to find the nth term numerically. I can see the structure. I can see the fiveness. I've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, repeated 5 times. And then underneath that, I've got 2, 2, 2, 2. So I must have n repeated 5 times plus 2. And then if I want to, I can say, okay, well, let's look at that numerically and say, well, how many ones are there in that first term? There are 7 ones in that first term. There are 12 ones in that second term. There are 17 ones in that third term. And so actually, I can look back and say, all right, well, yeah, this is based on the 5 times table because it's going up in 5s. So if it's 5 times, I can see it's 2 more than the 5 times table. 5, 10, 15, I can see it's 2 more than the 5 times table. But what I'm creating here is I'm creating this recognition that it's not just the fact that it goes up in 5s, and that's what allows me to find that 5n plus 2. It's about this structure that I'm choosing to look at and saying, right, well, if I relate this to this structure of 1, 2, 3, how does that relate? Well, I've got my rows of 1, my rows of 2, my rows of 3, and I have 5 of each of those, and then this 2 underneath. So in general, I'm going to have my 5 rows of n and this 2 underneath. And this approach goes beyond linear sequences. At some point, I'll get around to looking at quadratic sequences, and we can look at quadratics in a very similar way. And in fact, for quadratic sequences, this is potentially a much nicer in to quadratic sequences, particularly if they've seen it in linear sequences, than it is to examine them numerically. Because again, with quadratic, you can see the square structure underlying these terms. But we'll do another video about that at another time. Once again, and as always, I'd like to thank mathspot.com and its creator, Jonathan Hall, for providing such a great platform to use these virtual manipulatives that I'm using to create these videos. And if you are interested in the use of manipulatives and the use of visuals to support sense making of mathematical ideas, I would urge you to check out my website, visiblemaths.co.uk, and amongst the many things that you will find on there, you can find links to my book, Visible Maths, and some sample pages in there, and hopefully you'll order that book and find it useful. Thank you very much.